Hey, this is Horner. We're going to look at everything you need to know about rotational motion in order to pass the AP Physics test, Part 1. If you think about a circle, the distance all the way around a circular path, so if I go 360 degrees, we know that as the circumference. And we can find the circumference of any circle by finding the entire distance all the way around. So if I go all the way around the circle, that would be delta S. Sometimes you could also call that change in x. So sometimes they use s, sometimes they use x. That's their circumference. It's also 2 times pi times r, or 2 pi, and then we use a new term, and this term is called a radian. So what is a radian? A radian is basically just the angle that creates an arc. So here's an arc right here that is equal to the radius. So I have the radius. If I measured the distance from here to here along the curve, it would be exactly the same as the radius. So from the diagram, it's easy to see that it's a little bit less than 60 degrees. 45 would be here, so this is probably almost about 60. Or an equilateral triangle. So if I drew the other side of the triangle here, I have an equilateral, which means that all 3 sides are the same, with one of the sides that are curved. Pi is defined as the ratio of circumference to diameter. So we already know that the circumference is pi times the diameter. So one complete circumference is 360 degrees, so one radius would be 180 over pi degrees. So 1 radian is about what we see here. So just some background information on what you need to know. So if we want to convert from one thing to the other, for example, if I want to go from radians to degrees and I'm given 2.5 radians, all I do is multiply by 360 and divide by 2 pi. And if I do that, I get 143 degrees. So now I kind of know what 2.5 radians is. If I want to go from degrees to radians, I multiply by 2 pi and divide by 360, so I end up with 0.4014 radians. The first one that they want you to do is to convert 90 degrees to radians. So what I would tell you to do is stop the video at this point and actually try this one and see how you do. And then when you're done, come back. In fact, I'd do both number 1 and number 2. And then when you're done, I would come back and double check your answers. So I would pause now and then come back. All right, hopefully you paused. And so now let's go ahead and convert this one. We want 90 degrees. We want to go to radians, so we're going to multiply that by 2 pi radians all over 360 degrees. And radians is abbreviated with an RAD. So that's equal to about 1.57 radians. If I want to convert 6 radians to degrees, I'm going to start with 6 radians. And I'm going to multiply then by the inverse of what I have here, so that's 360 all over 2 pi, and that gives me 344 degrees. So pretty simple math, not anything that's earth-shattering, just a new way of looking at measuring angles. Angles are also measured in terms of revolutions, and so the conversion from radians to revolutions is you just take the revolution and multiply by 2 pi. Because we know that on a circle, if I go halfway around, that's pi, and if I go ahead and make my way all the way around, that's actually 2 pi. So I always say a pi or 2 pi. That is the question. That's terrible, I know. If I want to convert from RPM to radians per second, I usually will see rotational motion in revolutions per minute. And so I've got to go from revolutions per minute to radians per second. So I know that 1 revolution is 2 pi radians. I know 1 revolution per minute is equal to 2 pi over 60 because there's 60 seconds in a minute. So I can also say that 1 RPM is equal to pi over 30 radians per second. So they want us to go through and try to convert from 1.5 revolutions to both radians and to degrees. So we want to go from revolutions to radians and then to degrees. So to do the radians part, we're just going to do 1.5 revolutions, and we're going to multiply that by 2 pi radians per revolution. The revolutions cross off, and if I do all that math, I end up with 3 pi radians. A lot of times they'll leave these in terms of pi, since pi has a lot of digits after it, and we want it to be as exact as possible. The other thing they want us to do is go to degrees, so I'm going to start with 1.5 revolutions, and I know there are 360 degrees and 1 revolution, so that gives me 540 degrees. So if you've ever watched skateboarding, or if you've ever watched when they're trying to do snowboarding on the pipe, on the half pipe, they'll say they pulled a 540, and that's where that comes from, is it's 1.5 revolutions. 1 revolution would be a 360. So that's kind of what you would see. Velocity and acceleration is the next part. So rotational kinematics is really very, very similar to just regular kinematics. And remember, kinematics does things like velocity is equal to change in position over change in time. So that is the way that we used to do it. So we call this linear motion, and sometimes we call this translational motion, because I translate. I go from here in a straight line to this point. So that's linear, or we call it translational because I've translated from one place to the other. When I look at rotational motion, we're going to talk about something different. This little symbol is called omega, and it is the same type of thing as what velocity is, but omega is in a circle. So the other thing that you'll notice is it looks like somebody's sitting down. So I like to call this the butt. It makes it a little bit easier to handle these things. And this is equal to the final angle minus the original angle divided by the change in time. So it's just change in angle over change in time. Now, when we did direction for linear motion, we said this is going to the right, this is going to the left. And so when we do angular motion, if something is rotating clockwise, okay, we say that that is in the negative direction. So that'd be similar to going left. If something is rotating counterclockwise, then we say that that's positive. And that would be similar to something that's traveling towards the right side. So just something that you need to think about. This is a little bit counterintuitive because clockwise is negative. You would think it'd be positive. It's not. Clockwise is positive. Counterclockwise here is negative. So I like to say, you think about old people. Old people would rather see the clock turn backwards and go back to the way they were instead of moving on, and they're getting older and it's a little harder to get out of bed and you start to kind of look funny and you lose your hair and things. People would rather look younger. So I always say counterclockwise is positive because people do want that fountain of youth. They want to go back and look and see how things are better. So finally, the direction of angular vectors is measured by using the right-hand rule. So we'll talk a little bit about the right-hand rule in class so that you can see it. So the next thing we need to do is take a look at some example problems. And the first one here says a record spins on a phonograph. So you've seen the vinyl records and you know what a record player is. And it spins at 33 revolutions per minute and it goes clockwise. They want us to find the angular velocity. So it's traveling at a constant speed. It's moving around in a clockwise direction like this. And so right off the bat, we know our final answer should be negative. They want us to find the angular velocity for the record. So we know that but, or angular velocity, is equal to the change in the angle divided by the change in time. And they said that it was negative 33 revolutions per 1 minute. So that one was pretty easy to do. Our problem is we don't want it in revolutions per minute. We actually need this in radians per second. Those are our standard units. So our standard units are radians and seconds. So that is our SI standard unit for rotational velocity. So this is negative 33 revolutions for every 1 minute. And now I'm going to do my dimensional analysis because that's the best way to do it. 1 minute is 60 seconds. And then I have 2 pi radians for every 1 revolution. Now my revolutions cross off, my minutes cross off, and I'm left with radians over seconds. And if you do that math, you should get negative 3.46 radians for every second. The next problem is a little bit more difficult to do just because you've got to think a little bit more about this one on the front end. So it says find the magnitude of the Earth's angular velocity in radians per second. So we know the Earth rotates once every 24 hours. So here we go again. We've got omega is equal to the change in the angle over the change in time. And remember, we're going all the way around. So we're going to start, we're going to go do all the way around, go behind, and then it comes back around. If we looked at it from the top, we would know that we go all the way around, so that would be 1 revolution. So 1 revolution, and that's for every 24 hours. We need to convert this over now to our standard unit. So here, because I have 24 hours, I know that in 1 hour, I have 3,600 seconds, and I know in 1 revolution, I have 2 pi radians. So if you do your math, when you get done, you get about 7.27 times 10 to the negative 5th radians per second. So pretty simple to do. Next page here, or next part, is thinking about acceleration. So acceleration is very easy to do. You've done that before. Linear acceleration, so this is our linear. We also said that this could be what we call translational. So let's say that you get in your souped up sports car. Here's your souped up sports car, and you accelerate in this direction, and you go from 0 to 60 miles per hour, and you do that in 5 seconds. We could find out what your acceleration is by finding the change in velocity over the change in time. Angular acceleration would measure how fast you start to turn. So that would how fast you're turning and speeding up as you turn. So angular acceleration, we give it a term that's very close to A, but instead we're going to use alpha, and it does look like a fish. So I say this is the fish, and if you've ever gone fishing, we know that you sit on your butt for a long period of time. So that makes it really easy to see. If I'm going fishing, I'm going to sit on my butt for a very long period of time. The units for this are radians per second squared, and it's the rate of change of an object's angular velocity. So we're just saying how quickly we're picking up speed. It's positive for things that are going counterclockwise again, and it's negative for things that are increasing in the clockwise direction. All right, so let's try it and let's see if we can actually do this. So we're looking at the acceleration. It says a frog rides a unicycle. I don't know why the frog is riding a unicycle, but it is. If the unicycle begins at rest and accelerates uniformly in the counterclockwise direction, so we know that our acceleration, our alpha, is going in this direction, which means that it's positive, to an angular velocity of 15 revolutions per minute, per minutes, I guess that's what this is, in a time of 6 seconds, find the angular acceleration of the unicycle wheel. So first thing we need to do is take this 15 revolutions per minute. We know that we went from our change and our angular speed here is our final is 15, our original is 0, so that gives us a change of 15. So that we've already done, so that's revolutions per minute. We need to take this revolutions per minute and we need to make sure that we have it in radians per second. So in 1 minute, I do have 60 seconds. And for 1 revolution, I do have 2 pi radians. So that's pretty easy. So this is 1.57 radians per second. So here we go. Our angular acceleration, alpha, there's our fish, is equal to the change in omega. There's us sitting on our butt over a period of time. And so this is omega minus omega original all over time. We said that that's 1.57 radians per second minus 0 all over 6 seconds. And so we get 0.26 radians per second squared. So just like really simple acceleration problems we did for translational or linear motion, but now we just have to get used to the new units, and the new units are radians, and we still are using second squared on the bottom. So now we've got all the variables that we need to do a lot of different problems. And so here we go. We've got displacement as the change in s, or I think we're more used to the change in x. For angular, it's the change in omega. Velocity is v, or it's omega here. Sorry, change in theta. This is omega here. And we call that lovingly but acceleration, which is alpha or fish. And then we have time, and time doesn't change. Yeah, so it's really straightforward here. If I want to know what my different things are that I want to solve for, usually we're using x here. So x is equal to the angle times the radius. So if I want to go from translational and angular variables, if I want to go from one to the other, the best way to do it is to use the equations you see here. So if I want to go from, let's say that I have a curve, okay, I have a circle all the way around, and I want to know what is the distance along this curve right here. So I want to go from here to here. In order to solve that, what I can do is I can find the angle, and I can take the angle and multiply that times the radius, and that will give me the length of this arc. So that's what this equation does. If I want to know the velocity of something, and I already know how fast it's rotating in this direction, I know this value, then if I want the velocity in a straight line that would produce, I just take my angular times the radius. If I know what the acceleration is, and I want the linear acceleration of that object, I just take my angular quantity and multiply it times the radius. So all of these, notice the only thing I did was I took the angular quantity, whether it be the angle, the speed, or the acceleration, and I just multiply it times the radius. And when I do that, I get the linear thing. I can also then, if I want the angular thing, let's say that I know I went from here to here and I had a wheel that did that. I want to know how much of this arc this line represents. All I do is I take this distance and I divide it by the radius, and that gives me how far I went along this circle. So it's probably about like that for that line. Velocity and acceleration work exactly the same way, so same type of thing. So just a pretty basic thing for you to see. So now they want us to try it on our own. So there's a few problems here that we're going to try to do. The very first one is I've got a knight. It's swinging a mace. A mace was a medieval type of weapon where you had a spiky, really heavy ball on the end of a chain, and then you would swing that thing around your head, and then you would try to hit things with it. So they swing this mace of radius 1 meter in 2 complete revolutions. So here I've really just got 2 revolutions. They want to know what is the translational displacement. So when they swing it around twice, so it goes around 2 times, if I had a piece of yarn and I followed it and then I stretched that yarn out, I want to know how long is that piece of yarn. That's essentially what we're trying to do here. So here we're going to say that the change in position should be equal to the angle that we're doing times the radius. Here we know that we have the radius, and that radius is 1 meter. So we know that this is 1 meter, and then it says it goes 2 complete revolutions. So let's do the 2 revolutions first. 2 revolutions, and we want to convert from revolutions to radians, so that'd be 2 pi radians. So that is equal to 4 pi radians. So there's our angle change. So this would be 4 pi radians times that 1 meter, and I end up with 12.6 meters. So when it goes around twice, that's equal to 12.6 meters of length. Here this guy's listening to a big boom box, and there's a CD player on the inside, and the CD player will vary the disk rotational velocity so that the point being read moves at 1.25 meters per second. So if I look on the CD and I see that it's reading this portion right here, this curve, and I know that that curve is moving in a straight line, if I would make it straight, at 1.25 meters per second. They want us to find out what is the rotational velocity and revolutions per second. So we're finding revolutions per second. And it says when the laser is reading information on the inner portion of the disk, that is 0.3 meters. So that would be our radius right here. So there's our radius to that point that's being read. First thing we need to do is use our equation. The angular speed is equal to the velocity divided by the radius. So we're going from linear speed to angular speed. So we need to take 1.25 and we're going to divide that by the radius, which we said was 0.03, and that's equal to 41.7 radians per second. Now we need to take that 41.7 radians per second, and they want to know how many revolutions that is. So 41.7 radians per second. And we want to go to revolutions. So we know that for every 1 revolution, we have 2 pi radians. And it's already in seconds, so we don't have to convert it. And that would give us 6.63 revolutions per second. The next problem says, what is the rotational velocity of a compact disk? So the rotational velocity of a compact disk in the previous problem on the outermost portion of the disk itself. And so what we're going to do here is, I'm going to pick up my pen again. We're going to say that the angular speed, I've changed size. There we go. So our angular speed here, oops, that's not right either. Our angular speed is equal to the translational speed divided by the radius. So that's 1.25 meters per second, all divided by 0.06 meters, and that's equal to 20.8 radians per second. And now we need to convert that radians per second to revolutions per second. So we're going to take radians per second. So this is a radian. We're going to move the second down here. And now I've got 2 pi radians in every 1 revolution. And so that would be 3.32 revolutions per second. This is the end of the first of the videos. Next video, we're going to look at rotational kinematic equations.